Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Packed columns, packing, types, application and selection, part 2, packing and distributors. In this video, you will learn the different types of packing, characteristic stroke parameters of different types of packing, their applications and selection, types of distributors, application and selection. Please subscribe to the channel. By subscribing, you will motivate us to produce more knowledgeable video content for you. So subscribe now before you forget. Tower internals. The first step in the design of packed column is to select the type and size of packing as well as the distributors. Before you start designing packed column, it is important that you have knowledge about the types of packing and distributors available to select from, the sizes of the packing that fit into application and engineering requirement. Several design parameters are kept in mind when selecting type and size of packing and type of distributors. The key design parameters to be considered shall include HETP, pressure drop per meter of packing height, operating pressure, fouling and corrosive nature of the process. HETP directly affects the height of the bed required for a given separation. Hence, it is an important parameter along with pressure drop. We will discuss first the type of packings. Packing are divided into two types: random packing and structured packing. Random packing. Random packing has evolved over the years. From the year 1950 to early 2000, the industry has seen emergence of several types of random packing. Random packing are distributed randomly in the interior of the column. They are sometimes called dumped packing. They are easy to handle and filling into the column is easy. Random packing is available in different designs and shapes. Random packing fall into two broad categories. 1. Ring types. 2. Saddle types. Random packing under ring types include Rashik ring, Paul rings, cascaded mini rings, and nutter rings. Random packing under saddle types include ball saddles, interlocks metal tower packing, flexi mags. This figure illustrates some of the most widely used random packings in the industry. Observe the changes in shape of packing. Ring type shape is strikingly different from saddle type. Raschig rings and Paul rings are cylindrical in shape. The only difference between them is that the Paul rings have grooves made on the surface of the ring to increase the surface area of contact and improve the distribution of the liquid. Raschig rings are cheaper than Paul ring or saddles but are less efficient, and the total cost of the column will be higher. CMR, IMTP, Nutter rings and Fleximax etc. are improved version of ring type packing. They all have larger surface area and improved distribution of liquid compared to Paul ring. This table presents the characteristics of saddle tape random packings. Packing data presented include the material of construction of the packing, the size of packing, packing factor, surface area per unit volume of packing, and porosity. We discussed these characteristics in detail in part 1 of this video course. Note, interlock saddles has superior characteristics in terms of surface area and packing factor as compared with similar sized bell saddles. This table presents the characteristics of ring type random packing. Note the vastly improved packing characteristics of Paul ring compared to Raschig ring of similar size. This table presents the characteristics of the advanced ring type random packings, which are also called the fourth generation packing. You may observe the surface area per unit volume of CMR, IMTP and Nutter rings are comparatively larger than Paul ring and bell saddles. IMTP has the largest area among the fourth generation packings and hence more efficient. Likewise, the pressure drop parameter represented by the packing factor is less compared to Paul rings and saddles. The advantage of ring type packing is that it can handle large flux, but its disadvantage is bad distribution of liquid. The advantage of saddle type packing is good liquid distribution, but its disadvantage is that it can handle only small flux. Interlock saddles combines the advantages of both ring and saddle types, and hence its wider acceptance by the industry. Size of packing to be selected depends on the column diameter. For most applications, 38 mm and 50 mm, that is number 2 and 2.5 packing are usually used. Lower sizes of 25 mm are used in applications that needs greater efficiency but at the cost of high pressure drop. Lower sizes are costlier. Structured packing. Structured packings have been developed and used in distillation process for several decades. They are the preferred choice when high specific surface and low pressure drop are the key determining factors. Structured packing was first developed in early 1950s in wavy form and has undergone transformation over the last 5 to 6 decades. The most widely used structured packing is the third generation structured packing in corrugated metal sheet form. This packing has vastly improved performance characteristics such as high capacity and low pressure drop. These packing have become competitive and has gained wide acceptance by refining and petrochemical plants for a variety of applications, both for new installations and for revamps. Each layer of structured packing with a geometric structure of corrugated sheet consists of several individual sheets arranged in parallel and fabricated to fit the diameter of the column. Shown on the left is one layer of packing. For example, a column having inside diameter of 1000 mm will need structured packing with a diameter of 1000 mm. Shown on the left is a 1000 mm dia structured packing designed to fit into 1000 mm dia column. Several layers of structured packing with uniform height are arranged one above the other with the successive layer positioned at an orientation of 90 degrees as shown on the left. This is done so that the liquid and vapor follow a zigzag path as they flow through the packing. An important characteristic of the structured packing is that it spreads the liquid evenly as a thin film on its surface. The thin film so formed provides as much an active area as possible for the vapor-liquid contact for mass transfer. The net result is improved packing efficiency. This table presents packing parameters of some of the conventional structured packing used in the industry. Details provided are for wide type packing with crimp angle 45. The important parameters are packing factor, surface area, porosity, and HETP. Packing factor FP is pressure drop factor. Note, as the packing number increases, the surface area of the packing and pressure drop increases and the HETP decreases. Lower HETP means higher efficiency. Random packing versus structured packing. It is important to understand the advantages and limitations of random and structured packing. Notable points of random packing from application point of view. Random packing have flow channels which do not have fixed shape. They vary in nominal size from half an inch to 4 inches, made of ceramic and metal or plastic. They are cheaper than structured packing. They are easy to transport. They are dumped randomly from the top into the column. Notable points of structured packing from application point of view. It is manufactured in modular form to permit stacking in an orderly manner in the column. The height of each module can be varied from 6 inches to 12 inches. Have a surface area larger than random packing, made of ceramic and stainless steel. Transportation is difficult without damaging the shape, hence need special packing arrangement. Random packing is recommended when the fluids handled are corrosive, fouling and foaming in nature. They can be taken out from the column and cleaned and recharged to the column. Structured packing, on the other hand, are preferred in the following cases: when column operating under vacuum and when low pressure drop or low liquid holdup is required. For low pressure systems, structured packing provides the best efficiency. If fouled, the packing layer have to be replaced. There is no way you can clean the packing. From the above discussion on random packing and structured packing, it is obvious that the knowledge of relevant packing parameters and types of packing guide us to select the right size and type of packing for a given service right in the commencement of the design process. Distributors. How many of you pay attention to distributors in packed column? Liquid distributors affect to a great extent the performance of packing for a specific separation. Selection and proper design of liquid distributors plays a key role in achieving the intended design results. What is the role of distributors? Why is right distributor selection and its design an important engineering requirement? Let us find out. Selection of right type and size of packing does not by itself guarantee that the packed column will perform as per the design objective. Uniform wetting by liquid of the packing surface is equally important consideration. Simply spraying or allowing the liquid to fall on the top layer of packing does not lead to uniform wetting and film formation. The liquid has to be metered and distributed by properly designed distributors. The number of theoretical stages (NTS) and mechanical design of the liquid distributor combined together determine what depth of packing is required to give a specified separation performance. NTS, the number of theoretical stages, can be determined from the equilibrium and operating data liquid vapor ratio. It is a mechanical design of the distributor that influences the packed bed efficiency. The packing's mass transfer capability does not change. Poor liquid distributor design affects uniform distribution of liquid and causes a localized change in the L by B ratio across a bed and thus causes the loss in separation efficiency. The design and choice of distributor depends on several factors, which includes, amongst others, the quality of liquid handled. Presence of solids can clog the distributor holes and lead to maldistribution. This figure illustrates the effect of operating LVB ratio. The figure A illustrates the normal tower operation with the liquid getting uniformly distributed, and the LVB ratio is uniform across the cross section of the tower. Figure B illustrates the mole distribution of liquid and some section of the packing not getting liquid, so the LVB ratio is minimum or even less than that, causing a pinch. The above graphical illustration explains the significance of distributor selection and design for separation in packed column. Liquid distributors used in distillation columns are in general of orifice type. The key design parameters of the liquid distributor that ensures that the quantity that leaves every orifice or hole in the distributor is uniform are 1. The diameter of the orifice or the holes. 2. The head or the driving force in the distributor. This figure illustrates some of the commonly used distributors for packed column. A is a spray nozzle distributor. B. Orifice pan distributor. C. Trough and tom distributor. D. Trough and tom distributor for clogging service. Key takeaways. Remember the golden rule. Do it right in the beginning. Have an understanding of the nature of the process and the key operating parameters. Select the type and size of packing that meets the engineering requirement by comparing the packing parameters. Select the right type of distributor and design it as per design guidelines based on column loading data. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.